and their decimal expansion. Rational and irrational number, we can study them in terms of real numbers and their decimal expansions. We'll try to look at the decimal expansion of real number, and then we also try to see if we can use the expansion to distinguish between rationals and irrational. Is it possible? And how to visualize the representation of real numbers on the number line using their decimal expansion. Because a rational number is quite familiar to us, we know that p by q form is our rational number. So 10 by 3, 7 by 8, 1 by 7. Let us take these examples, right? Just you have to be a little considerate about the, or very much attentive about the remainders. See, this is 10 by 3. I am dividing the 10 by 3. So 3 3s are 9, 1, and I take a point, then 0, decimal 0. 3 6 are 9. Again, it goes on and on. Like, so this is 3.3, and this goes on and on and on. Now 0.875, because this is 7 divided by 8, so I have to take a 0 so that I can have a 0 here. So 7, 8 is a 64, then 6, 0, then 8, 7 is a 56, then 4 is remainder, 5 is a 40, then 0 is the remainder. So this is completely divisible, no problem with that. Now 1 divided by 7, let us take 0 again, so I get 10, I put a point, 7 ones are 7, 3 remains, and I go on and on. So I have now different numbers, they are not recurring. 3 is repeating, 3 3 3, this has finished, but these are the numbers which are repeating, but they are not recurring. Same number is not repeating like this. So what you have noticed, as I just said, you have to consider very much attentively about the remainder. So the remainder either becomes 0 as in 0.875, or it starts repeating itself. So the number of entries in the repeating string of remainder is less than the divisor, that is 1 by 3, because the number repeats itself and divisor is 3. In 1 by 7 there are 6 entries, 3 2 6 4 5 1 in the repeating string of remainder, and 7 is the divisor. If the remainder repeat, then we get a repeating block of digit in the question, like 1 by 3 repeats in the question, and 1 by 7 this repeating block is 1 1 4 2 8 5 7. If you do it again, see, 1, you started with 1, again you came back to 1, so again you will have 1 4 2 8 5 7. This is repeating, so this goes on and on. So this is what I am trying to tell, that we have noticed that this pattern, in this example, it is true for all rational number of p by q. Either you will divide it, either there will be same number repeating, or there will not be numbers which are repeating. So on division of p by q, two main things has happened. Either the remainder becomes 0 or never becomes 0. It will repeat again and again. So let us take case 1, the remainder becomes 0. So 7 by 8, we saw that 7 by 8, 0.875, so which is equal to a number which has finished, and 8 has actually divided 7. 1 by 2 is 0.5, this number also 2.556. So in all the cases, the decimal expansion terminates and end after a finite number of steps. We call this kind of division, or we call the decimal expansion of such number as terminating. Now the case 2 is the remainder never becomes 0. See, 1 by 3 and 1 by 7, we have already seen the division of these. This 3 will never stop. This 1 4 2 8 5 7, 1 4 2 8 5 7, 1 4 2 8 5 7 will never stop. It will go infinite. It will go infinite. There is no ending, right? We have repeating blocks of digit. We have repeating block of digit in the question, and we call that this expansion is non-terminating recurring, because it is not terminating and recurring also. This is repeating. So the usual way of showing these 3 repeats in the question is not 0.333333. We stop this and we just take a bar on this. So 0.3. In the similar fashion, 142,857 repeats for 1 by 7. So we just put a bar on 142,857, right? Where the bar above the digits, it is going to indicate the block of digit that repeats. In this case, we have 572, right? And then 7270 repeats. Till the time 5 is there, no problem, 7272 repeats. So this is a non-terminating recurring decimal expansion. So we have seen that the decimal expansion of rational number, they have only two choices. They are either terminating or non-terminating recurring. But let us walk on the number line again. When we come across any number 3.14268, this is actually pi, whose decimal expansion is terminating, right? Or a number like this one, that is 1.272727, it is the decimal expansion is non-terminating recurring. How can you say, or what can you say about this number being rational number? Can you conclude this number as a rational number? Yes. The answer is yes. If something terminates like this, it is a rational number. If something repeats, because 1 by 7 is a rational number, 1 by 3 is a rational number, right? So these are rational number. Okay. We have to show that 3.14267 is a rational number, or you have to say that this is in the form of p by q. I take this as divide by 0, that is 3.14268, because this decimal 1, 2, 3, 4, 5, 6. So I have 6 zeros here. This is a rational number. It can be represented in p by q form. Now let us take those decimal expansion which are non-terminating recurring. That means 0.333, 0.3. This can be represented by p by q. How? See, we don't know 0.3 what it is. So let us consider x equal to, we can just say this as x. Now multiply both the sides by 10, say 10. So what do you get? This 10x, and you multiply this by 10, so this becomes 3.333. Now see, first of all, this is 3.333, so you can write it as 3 plus 0.333, but you have taken x as 0.333, so in this case you can write x in this place. So 3.333 can be written as 3 plus x. So 10x will become 3 plus x. Now take x here. This is 9x. X is 3 by 9, so you get 1 by 3. So if 0.333 is given, you can easily find out the p by q form. In the similar case, you have 1.272727 is 1.27 bar, and you have to express this in p by q form. So x is this, right? Let us, because this is repeating, 27 is repeating, so we have to multiply it by 100. In the previous case, because only one number is repeating, 333, we multiplied it by 10. Here we have 272727, so it is multiplied, means we have to multiply it, because 27 is repeating, we have to multiply it by 100. Let us multiply this by 100. So just both sides, x and this, I multiply 100 here, I multiply 100 here. So 100x will be equal to 127, because 100, this point will go on the right side to jump it will go. So 127.2727, but 127.277 can be written as 126 plus 1.2727, right? Because if you add this, you will get 127.27. Why I have done this? Because I need this again, because I have taken this as x. So 126 plus x, this can be written as x. Now x has to be put here. So 126 will be 100 x minus x. This will be 99x. X becomes 14 by 11. So this can be represented as p by q form. Now we have to show that 0.2353 means 2 is there, but 3535 is remaining, means repeating. So 0.235 you have to put in p by q form. So x equal to 0.235. Now you know that two numbers are repeating, so you have to multiply it by 100. So let us take x equal to 0.235, multiply both sides by 100. You get 23.53535. Either you multiply this with this, you get this, or you can say that I can represent 23.53535 is equal to 23.3, and 0.23535 I required this because I need x. So this is 23.3 plus x. Now let us take x on this side, 99x equal to 23.3. So 99x will be 23. You can take 10 down. So 233 by 10. Take 99 here. So 233 by 990. This is your x. This is your p by q form. So every number with a non-terminating recurring decimal expansion can be easily represented by p by q, as we just saw. So let us summarize what we have seen. Decimal expansion of a rational number can be either be terminating or non-terminating recurring. And also the number whose decimal expansion is terminating or non-terminating recurring is irrational. So these two means same thing we have said, vice versa. Now let us go, or let us learn that the decimal expansion of real number, what it can be. What about the decimal expansion of irrational number? These were all rational numbers. Because we have seen the property, we can conclude that any decimal expansion, if it is non-terminating, non-recurring. See, this was this is terminating or non-terminating, but here we are talking about non-terminating, and it is not recurring also. Means if you talk about irrational number, the decimal expansion of a irrational number is non-terminating and non-recurring. You can say a number whose decimal expansion is non-terminating, non-recurring is irrational number. This was the number s equal to 0.10 like this. See, this is 10, this is 110, this is 1110, 111110. So there is no repetition and there is no ending also. So this is a non-terminating, it is not terminating, and non-recurring because the numbers are not recurring. So because of this property, this number is irrational number. You can generate infinitely many irrational number which is similar to this one. How? We have a very famous irrational number, root 2 and pi. Root 2 is 1.4142. See, it goes on and on. Pi goes on and on. You don't know where it is going to end because it never ends, and the numbers never repeat. Never repeat. That is why these are irrational numbers. See, root 2, some great mathematician, they have tried to solve it also. Root 2 can be represented as 1 plus 1 by 3. So this was an approximation in Vedic age. Sulbha Sutras, rule of God, it was given. So they tried to put a number to it, right? This is very interesting, but let us consider root 2 always to be a rational number. Find an irrational number between 1 by 7 and 2 by 7. So 1 by 7 is this one and 2 by 7 is this one. You can just divide and find it out. This is quite easy. But in order to find the irrational number between these two, we can find number which is non-terminating, non-recurring, lying between them. We just want the number should not terminate and should not recur. So you can have number of these. See, 0.1, this starts from 0.14, this is 0.28. So 0.15 you take 150, 1500, 15000, 15000, like this. You can have other number as 150000 like this. So it can go on and on, you know. So this is the